Hey everyone, and welcome. Today, we're going to take this really cool journey to expand our whole universe of numbers. We're going to start with the absolute basics, just counting, and see how new problems forced us to literally invent new types of numbers. So, let's dive right in. So where do we start? Well, right at the very beginning, with the natural numbers. These are the first numbers any of us ever learn, right? The counting numbers. 1, 2, 3, and so on. They're what we use to count things. 1 rock, 2 trees, 3 people. Super simple, totally intuitive, and they are the absolute bedrock of everything we're going to talk about today. Okay, but what happens when you've counted all your sheep and then there are no sheep left to count? How do you represent, well, nothing? For that, we needed a brilliant invention, the number 0. And once you add 0 to the natural numbers, you get what we call whole numbers. It might not seem like a big deal, but adding a symbol for nothing was a massive leap in how we think about math. Now let's throw a wrench in the works. What if you owe someone $3? Or what if it gets really, really cold and the temperature drops below 0? All of a sudden, we need numbers that can handle ideas like debt or values that are less than nothing. And that's where integers come in. They include all the whole numbers plus their negative opposites. Our number line just got a whole lot bigger, stretching out to infinity in both directions. So, what's our game plan for today? First, we'll see why our number system had to keep growing. Then, we'll meet the stars of our show, the rational numbers. After that, we'll learn the rules of the game, how they behave. We'll uncover their special superpowers. And finally, we'll explore the totally mind-bending world that exists between the numbers we thought we knew. Okay, so we've got positives, negatives, and 0. That should pretty much cover everything, shouldn't it? Well, not quite. Turns out there's another everyday problem that our integers just can't handle on their own. Think about it. Integers are fantastic for counting whole pizzas. But what happens when you eat a slice, or you want to share it with a friend? Integers just fall apart. We need a new kind of number, a new tool in our toolbox that's designed to talk about the pieces, the parts, the fractions of things. And this is where the hero of our story steps in, the tool we needed to solve our pizza problem. It's time to officially meet the rational numbers. The official definition is actually pretty elegant. A number is rational if you can write it as a ratio, a fraction, of 2 integers, p over q. Simple enough. But, and this is a huge but, look closely at that last rule. The bottom number, q, can never ever be 0. Why? Because trying to divide by 0 is one of the few things in math that just plain breaks everything. It's undefined. Okay, let's make this real. So what counts? Obvious fractions like 1/2 or -3/7, yep, they're in. But what about a number like 8? It's rational too, because you can just write it as h over 1. Even 0 is rational. You can write it as 0 over 1. The only absolute deal breaker, the one thing that gets you kicked out of the club, is putting a 0 on the bottom. 5 over 0 isn't a number. It's just nonsense. All right, so we've got these new players on the field, but how do they play? What are the rules? Let's start with the basics. What happens when you add them together? Think of what's coming up as the official rulebook for rational numbers. First up is a big word for a super simple idea, commutativity. All this really means is that when you're adding, the order just doesn't matter. You already know this. 5 plus 2 is the same as 2 plus 5. And it turns out, this exact same rule works perfectly for fractions too. And you can see it right here in action. Whether we start with the -7/12 on the left, or we start with the 5/8 on the right, it doesn't make a difference. The path you take looks a little different, but you end up in the exact same spot, 1 over 24. It just works. Okay, next rule of the game, associativity. This one is all about grouping. It says that if you're adding a bunch of numbers together, say A, B, and C, it doesn't matter if you add the first 2 first or the last 2 first. You can regroup them however you want, and the answer will always be the same. And check it out. The math might look a little messy here, but the idea is crystal clear. On the top, they group the first 2 fractions together first. On the bottom, they group the second 2. And what happens? It doesn't matter. Both roads lead to the exact same place, -13 over 20. So, beyond these basic rules for how to add and subtract, some numbers have, well, they have special jobs. You can almost think of them as having superpowers. And for addition, the 2 most important are the identity and the inverse. All right, first up is the additive identity. Think of this as the number that's just neutral. The one that, when you add it to any other number, it doesn't do anything at all. It leaves the number exactly as it was. And for addition, that special number is, you guessed it, 0. And here it is. It's so simple, it's almost funny, right? 7/8 plus 0 is, well, it's still 7/8. Zero's superpower is to do nothing, and it does its job perfectly every time. It's a simple idea, but it's totally fundamental. So, if 0 is our neutral hero, every number also has a perfect opposite. It's called the additive inverse, and its job is to cancel the original number out completely, bringing the whole thing right back to our identity hero, 0. What's so cool about this is that it means no rational number is ever alone. For every single number, there's a partner, an inverse that can bring it back home to 0. You can see it right here. 7/8 plus its opposite, -7/8, equals 0. It's like a mathematical reset button. Okay, we've got the definition down, we've got the rules of the game. But now we get to the really wild part. The thing about rational numbers that is kind of mind-bending, just how many of them there are and where they live. So think about that classic number line. We know where the integers go. They're the big, clear tick marks. 0, 1, 2, -1, and so on. Well, rational numbers live in all the spaces in between those marks. Here you can see 1/2 sitting snugly right between 0 and 1, and -3/2 found its home between -1 and -2. And this leads us to a really fascinating question. Look at that little gap on the number line between 2 and 3. Seems like a tiny space, right? So how many of these rational numbers, these fractions, can we actually squeeze in there? A dozen? A few hundred? What do you think? We'll check out this super neat trick. You just take the two numbers, 2 and 3, and add them up. You get 5. Then you just divide that by 2, and boom, 2.5, or 5/2. We just found a number that lives smack dab in the middle of them. But here's the kicker. What's stopping us from doing the exact same thing again, but this time with 2 and 2.5? Nothing. We can just keep doing this over and over forever. And this leads us to a conclusion that is just staggering. Between any two rational numbers you can possibly name, I don't care how ridiculously close together they are, there isn't just 1,000 or 1,000,000 numbers. There is an infinite amount of other rational numbers packed in there. It's infinitely dense. So with an infinite number of these fractions crammed into every little nook and cranny, it really feels like we must have found every possible number, right? The number line should be completely full now, totally solid, with no gaps left at all, right? Well, what if I told you that even with this infinite density, there are still holes? Now that is a story for another time. Thanks for joining me on this one.